Hello maths fans! Dr Tom Crawford here at the University of Oxford, and today we're looking at the maths of ancient Egypt. This video was inspired by an article I read about the Great Pyramid of Giza, which explained how the base actually has 8 sides rather than the expected 4, and naturally I thought I would go and see it for myself. But of course that wasn't all that I discovered. In this video, we'll be looking at 3 main aspects of ancient Egyptian maths: the number system, the calendar, and the geometry they used in their magnificent architecture. We start where my journey began, in the city of Luxor and Karnak Temple. This site has been in use for over 4,000 years and is part of the monumental ancient city of Thebes, a UNESCO World Heritage Site. For most visitors, the most striking feature is the Great Hippo-style hall, consisting of an area of 5,000 square meters filled with 134 columns neatly arranged in 16 rows. And don't get me wrong, the columns in particular are fantastic, but that isn't why we're here. On the outside wall of one of the interior temples, there are actual carvings of numbers. A single straight line represents 1, and if you wanted to count up through 2, 3, 4, all the way up to 9, you would just use several repetitions of the straight line. So each of these represents 1 unit. Again, what we would refer to as the number 1. Then if you move up to 10, having written 9 straight lines, you then have what I would call a horseshoe, but what is more accurately referred to as a hobble for cattle. And this is going to represent 10. As with the single units, 9 of these would represent 90, and then the units would be given by the number of straight lines. We then move up to 100, which is represented by a coil of rope, and this represents 100, and once again we would count up through these, so you would have 200, 300, up to 9 coiled ropes representing 900, and then once you have 9 coiled ropes, 9 hobbles for cattle or horseshoes, much easier to remember them as horseshoes, and 9 scores or 9 units, we would of course have 999, and then we would move up to 1000. Now there is a symbol for 1000, I am not going to draw this, I will show you this on screen. 1000 is represented by a lotus flower. Then we go to 10,000, represented by a finger, 100,000 by a frog, and 1,000,000 represented by a god with his hands raised in adoration. Now I stopped at drawing the 100 symbol, the coiled rope, first of all because of my lack of artistic talent, but also because on the wall itself, as you can see in my video, I could not actually find any of the symbols for those higher numbers. So with these 3 symbols alone, we can actually decode everything that is shown on that interior temple wall. So if we look at the only column of numbers that contains the coiled rope and the 100 symbol, then as we read down the column, we actually have 3, 2, 6, 12, 4, 99, and finally 128. Now unfortunately, I'm not actually sure what this list of numbers represents, or more generally what any of the numbers on the temple wall actually represent. I did try to do some research to discover this, couldn't find the answer, and I did ask our guide, who also wasn't sure. But what I did discover, doing some research into ancient Egyptian numbers, was the really interesting method that they used to multiply numbers together, which was based on powers of 2. The way it works is to first break down the numbers you want to multiply into the powers of 2, or binary numbers that make them up. So for example, with the ones we have on the board, it might go as follows. 3 would be equal to 2, which is of course 2 to the power 1, plus 1, where 1 is going to be represented by 2 to the power 0. 2 is of course just 2, 6 would be 4. We take the largest power of 2 less than the number. So it would be 4 plus 2. So that would be 2 squared plus 2 to the power 1. 12 is going to be 8 plus 4. 4 is just going to be 4. 99 is going to be 64 plus 32. And then you're left with an additional 3, which is plus 2 plus 1. And then finally, 128 is actually a power of 2. So that's just 128. So let's suppose I want to multiply the number 128 by 7. So something that is reasonably difficult to do in your head. I'm sure you could all work this out, but let's use the ancient Egyptian method. So I want to calculate 128 and I want to multiply this by 7. So first of all, we want to think about how many powers of 2 do we actually have in 128. And again, I'm sure some of you will know this directly, but we actually need to go through that list by doubling each time. And you'll see why in a moment. So we would start at 1, 2, 4, 8, 16, 32, 64, and then we get to 128. So that would be 0, 1, 2, 3, 4, 5, 6, 7. So it's 2 to the power 7. But that's kind of irrelevant once we've got our list written out. Because if we want to multiply this number by 7, then what you would do following the ancient Egyptian method is you start with your number 7 and then you double it, because we doubled the 2, so now we double the 7. And then we double again. So it's very easy to double numbers, and this is what ancient Egyptian multiplication relied on. They found it much more straightforward to simply continue to double numbers than to multiply numbers by 7, for example. So we continue in this way, so then we get 56, double that, you get 112, you get 224, double that, you get 448, and then doubling 448 is going to give me 896, and now that is going to be my answer. Because we started with how many powers of 2 did it take to get to 128, and then what we've done is multiplied 7 by itself that same number of times, 128 times, to get 896, which is of course the correct answer. 128 times 7 is indeed 896. And this method will actually work when multiplying together any two numbers. You do not require one of the numbers to be a pure power of 2. We could instead take 99, having broken it up into its power of 2 decomposition, we then just add together those relevant pieces. So for example, suppose I want to do 7 multiplied by 99. And I'm just picking 7 again because we've already done some of the work over here. Again, that could be any number. So 7 times 99, the idea is, well, that's the same as 7 times 64 plus 32 plus 2 plus 1. And so we could, in theory, split these pieces up and say, well, that's 7 lots of 64 plus 7 lots of 32 plus 7 lots of 2 plus 7 lots of 1. Now, we already know the values of all of these 4 pieces because we just did our simple trick earlier of doubling 7 continually. So we need one lot of 7, so we need this one. We need a 7 times 2, that's going to be this one. We need a 7 times 32, which is down here. And we need a 7 times 64, which is this one. So we know the individual values of those pieces. So now we just have to add them up. So that's 448 plus 224 plus 14 plus 7. And that's going to give me, I'll do this step by step, 448 plus, that's 21, so that's plus 245. So now I can hopefully add those two together and get 693. So I believe using ancient Egyptian mathematics, their method of multiplication, 693 is 7 multiplied by 99. So now we have a better understanding of the number system used by the ancient Egyptians, we can move on to look at their calendar. And our next stop takes us south along the River Nile to Kom Temple, which is a beautiful temple in its own right, but it is probably more famous as the home of the mummified crocodiles. Over 300 crocodile mummies have been found at the site, which are likely linked to the southern half of the temple, which was dedicated to the worship of the crocodile god Sobek, the god of fertility and creator of the world, alongside Hathor and Khonsu. However, as cool as crocodile mummies are, and let's be honest, they are pretty cool, we are once again here for the maths. This wall at Kom Temple is the only known example still visible today of an ancient Egyptian festival calendar. The calendar consisted of 3 seasons, each made up of 4 months: the inundation or flooding season, Akhet, the growing season, Peret, and the harvest season, Shimu. Each month was made up of 30 days, which were then subdivided into 3 10-day periods called decans, which in some sense represented the modern day weeks, as the last 2 days of each decan were treated as a weekend where royal artisans would be free from work. The reason the wall at the Temple of Kom is so exciting is that if we look at the furthest right-hand column of the wall and we read down the page, we can see that the calendar is counting through the days of the final month of the harvest season. So starting at 23, 24, 25 through to day 29. And then we see more detailed hieroglyphs which detail the beginning of Akhet and the transition to the new year and the season of inundation. Now, if we look a little more closely at the maths of this calendar, we can see that it doesn't quite add up. So we have 3 seasons. We have Akhet, which is the season of flooding or the season of inundation. We have the season of growing, which is Peret, and then we have harvest, which is Shimu. Now, each of these consists of 4 months. So we have 4 months, 4 months and 4 months, and each month consists of 30 days. So that's 4 times 30, which is 120 days, 4 times 30, which is 120 days, and 4 times 30, which gives us another 120 days. Now, of course, the solar calendar, the time it takes for the Earth to orbit the Sun, is 365 and a quarter days. The quarter is, of course, the reason that we now have leap years in our current calendar. But here we have 360 days, so we are 5 and a quarter short. Now, the bulk of that was actually fixed by adding an additional 5, which were days outside of the traditional calendar, just added on at the end of the year to make everything line up. So that does give you your 365 days, kind of cheating a little bit by just adding in 5 at the end, but they did figure this out and add in those extra days that we needed. However, it is currently up for debate, shall we say, amongst historians as to how they dealt with the additional 1/4 of a day. So whilst currently we might not know exactly what they did to fix this issue, they must have done something, because even though 1/4 of a day sounds like a small amount to be out over the course of a year, that will actually build up and lead to quite significant changes in terms of when you start your new year. And given that the Egyptian calendar here was based on the seasons and based on agriculture, they are going to end up being quite far out. So for example, 1/4 of a day out in 1 year means that after 4 years, your calendar, or your solar calendar versus your calendar, is out by a day. So not too big of a deal, as perhaps you harvest your crops a tiny bit earlier, a day earlier, or your winter, you believe, ends a day earlier than it does. So not a huge deal at this point. However, after 120 years, so 30 lots of this, you're now out by a month. And so being out by a month could have quite a drastic effect on when you're harvesting your crops. They might not be ready yet, or the flooding may come sooner than you realized. And if you continue in this way, then after 12 times 120 years, so that's going to be after 1,460 years. I should have done some ancient Egyptian maths to work that one out. The 1,460 years, you're actually going to be out by an entire year. Which I suppose isn't too much of an issue because you're back where you started, so you're back on schedule. But of course, in between, at 730 years, in the middle, you're going to be exactly out by 6 months. So you're going to think it's winter when it's summer, and the other way around. So whilst the initial error of a quarter of a day doesn't appear to be a huge issue, if it is left unchecked over the course of a civilization, such as the ancient Egyptians who were around for several thousands of years, it could generate huge problems. So whilst we don't know exactly what they did to fix this, they must have done something. So far, we've already seen examples of the fantastic architecture in ancient Egyptian temples, but the civilization is perhaps most famous for its tombs. From the Valley of the Kings to the Great Pyramids of Giza, the most impressive ancient Egyptian structures that remain were used to house the dead. When visiting the Valley of the Kings, I was particularly interested in the numbering system that was used on the tombs. So for example, the tomb of Tutankhamun was labelled KV62. This system can in fact be traced back to Sir John Gardner Wilkinson, often referred to as the father of British Egyptology, who in 1827 painted numbers KVXX above each entrance to the tombs open at the time. As new tombs were discovered, the numbers increased sequentially up to KV64, which was the most recently discovered tomb in 2011. During my visit, we were able to see the interior of KV7, which belonged to Ramses II, KV11, which belonged to Ramses III, and KV17, belonging to Seti I and the longest tomb in the valley. We also paid for an extra ticket to visit KV62, the infamous tomb of Tutankhamun. The tombs that are open to visitors change regularly, so no doubt I will be back to see how many more I can tick off the list. For the final stop of our mathematical tour of ancient Egypt, we go to the most famous, the Great Pyramids of Giza. As I mentioned at the beginning of the video, the largest pyramid consists of 8 sides, which is so subtle that it can only clearly be deduced from the air. In fact, it was discovered by accident in 1940 when a British Air Force pilot, P. Groves, was flying over the pyramid. He happened to notice the concave sides and captured them on camera. Whilst the Great Pyramids of Giza are undoubtedly the most impressive, the oldest is in fact the Pyramid of Djoser at Saqqara. This is located south of Cairo, near to the ancient city of Memphis. The Pyramid of Djoser is a step pyramid with a height of 62.5 meters and a base measuring 121 meters by 109 meters. So, what's the volume? We start by drawing a picture. So if we model this to begin with as a slanted or regular sided pyramid, and we will look in more detail at the steps shortly. But to begin with, let's suppose we have our slanted sides, and then we're going to have the base, which is going to be a rectangle in this instant. So again, as usual, forgive my artistic talent or lack thereof. That one's going to be in the back. I'm going to have this one coming down to here. That's not too bad. So we have a rectangular based pyramid. And we will assume, as I mentioned, that this is regular. So rectangular based pyramid. And we know all of the measurements. So we know that the height of the pyramid here is going to be 62.5 meters. And then we know that the base is 121 meters by 109 meters. So the volume of this volume of the rectangular base pyramid is simply given by multiplying the three numbers together. So we have our three dimensions. So it's going to be 62.5 times 109 times 121. But of course, that would give us a cuboid. So we have this pyramidal shape instead of a cuboid. So we actually have to divide by 3. And this again is because this is a regular pyramid with slanted sides. And by fixing the height, we are fixing the angle between the base and the peak. So this gives us an answer of around 275,000 meters cubed. Now suppose we want to be more accurate with our estimate of the volume, and we want to include the step-like behavior or the step-like shape of the Pyramid of Djoser. If we look at some images, we can see that there are a total of 6 steps, and the top of the pyramid is in fact flat. So the shape would be something more, or at least the cross-section would look something more like so. That'd be 1, 2, 3, 4, 5. And then the one at the bottom is actually a little bit bigger than the others. And this is going to be important. So from the side view of the pyramid, this is very much a 2D slice. We have 6 cuboids or 6 rectangles from the 2D, but they will of course be cuboids with that additional dimension. So if we want to know the volume of this, we need to work out the volume of these 6 individual pieces. Now, before we do that, I'm going to pose a question for all of you as the viewers. Do you think the volume of the step pyramid will be larger or smaller than the volume of the regular slanted pyramid that we've already calculated? So when we work this out, will this give a larger value than 275,000, or will it give a smaller value? Hold that thought and we can check it at the end once we have our hopefully more accurate estimate for the volume of the Pyramid of Djoser. Before we begin our calculation, we need to decide how to split up the height of the pyramid. So we know the total height is 62.5 meters. We know that there are 6 steps, 6 layers based on all of the images. And the other thing that I hinted at that we can learn from those images is that the very bottom layer is actually a little bit bigger than the others, which are approximately the same size. So given the numbers we have to work with, what I'm going to do is say this is going to be a height of 12.5, and then each layer from that point onwards is actually going to be a height of 10. So this is saying the 6 layers are approximately the same size, apart from the one at the bottom, which is a little bit bigger. And again, if you look at some of the images, this is a reasonable model for the approximate volume of the pyramid. Okay, now we can start calculating. So for the bottom piece, we know that we have a cuboid shape, and we also know the area of the base because it's unchanged. It's still 109 by 121. So if we say sort of cuboid 1, meaning the one on the very bottom, level 1, then we know that that is, let's call it A, where A is the standard base size. So A is 121 by 109, which of course we could work out using some Egyptian maths probably, but I'll just call that A, is the area of the bottom multiplied by the height, which is 12.5. So that's A times 12.5, and that will be meters cubed, will give us the volume of this lower cuboid. Now for the second cuboid, the second level, we know the height, it's 10, but what we don't know is the size of the base. So we can see that it's smaller. It does not contain the full dimension, so we expect something smaller than A as the area of our base. And it's going to be reduced on all 4 sides. Now, how do we work this out? Well, the trick here, and I'm going to use a different color to emphasize this, the trick here is to think about similar triangles. So if I add in my peak, and I'm going to attempt to make this accurate, though it might not be. Having now added the outline of a regular pyramid shape to our diagram of the step pyramid, we can now actually answer two questions. So first of all, we can see that the step pyramid will have a larger volume, to come back to my earlier question. So we're expecting a larger answer than what we got here, approximating as the straight-edged pyramid. And secondly, we can importantly see how the slanted side of our pyramid is related to the new length of our second level base. And what I mean by that is hopefully best demonstrated by a separate diagram. So, what we've got as a cross section sort of through, let's say, the left-hand side of our pyramid is we have a right-angled triangle. Now, this is sort of this section here, the original pyramid shape, and this is our right angle. Now, the angle here, theta, we can work this out. So we know the bottom is, let's take the long side, for example. So it's 121, so this is 60.5 across here, and we know that the height is 62.5 total. So writing them over here, we know this is 60.5, this is 62.5, and we have an angle theta. So tan of theta is equal to opposite over adjacent, so we can work that out. It's going to be a little bit bigger than 45 degrees because this is going to be a little bit bigger than 1, and tan of 45 degrees is 1. So we've got an angle a little bit steeper than 45 degrees. Now, that's actually kind of irrelevant because when we go to the next level, think about what's happened. And again, I should use a different color. We come down and then we go across. So now we have this right angle triangle and we have the same theta. This hasn't changed. This red triangle is a similar triangle to the yellow one. So now we've got triangle over here, the same angle theta. We now know the new height is given by 50. And so by whatever scaling factor we have used to shrink 62.5 down to 50, we know that the base will shrink by the exact same scaling factor precisely because these are similar triangles. To go from 62.5 to 50, we have multiplied by 0.8. So 50 is actually 80% of 62.5 because a quarter of 50 is 12.5, and we've added that. So what we're doing in step 2 is actually shrinking the height by 20%, so 0.8 on the height. So that means we're shrinking in by 0.8 on all of the other dimensions. And of course, this is symmetric, so the same for this triangle. So we now know that the new area is the original one that we had, but the 121 has been multiplied now by 0.8, and the 109 has been multiplied by 0.8. So it's the original area times 0.8 squared, so that's actually 0.64 times that original area A. That gives us the area of the base, and then we have to just multiply by, so the volume, that's the area, so the volume is then just 10 times that, so 6.4 times A. So up here we get 12.5 times A, and this one is 6.4 times A, so it is about half as much, in fact, of the volume of the bottom cuboid. For the third cuboid, we proceed in pretty much the same way. And what I mean by that is we work out by what scale factor have we multiplied by to get the new triangle. So before we had a height of 50, now on the third one, what are we left with? We had a height of 50, we now have a height of 40, and so we've actually gone from 50 to 40, we've multiplied by 0.8 once again. So it's 0.8, so we previously had the area of the base as 0.64a, so the new area, or the new volume, if I do it properly, is the height times 0.8 squared, one factor for each dimension in that base, multiplied by the old one, which is 0.64a. So when you compute those numbers, what you'll actually get there is 0.4096 times a, where again, a is the original base. So this one is about 40% of the volume of that original first cuboid. And the others are going to proceed in the same way. So we, thinking about it from here to here, this was 0.8 factor. From 2 to 3 was also 0.8. Now we go from a height of 40 to a height of 30. So that is a factor of 0.75. The factor changes at this stage. So we then go times 0.75. Then we go from a height of 30 to a height of 20. So that's times 2/3 or times 0.67. And then finally we go from a height of 20 to a height of 10. So we're going to multiply by a half. So this is the single scale factor of how the height is being rescaled of that triangle. So we have to square that to rescale the area of the base. So putting everything together, we can say that the volume is equal to the sum of the volumes of the cuboids. We know the first one is 12.5a. So we're going to have this common factor of a outside. And then we've got 12.5 from the first cuboid. Then we saw that we had 6.4 lots of a for the second one. So plus 6.4. Then for the next one we had, when we multiply by 10, I forgot to do that, we're going to get 4.096a. So that's 4.096a. Then, so that one was having done this one, so we've done this one, this one, this one. Now we have to do 0.75 squared multiplied by this number and then multiplied by 10. So that's going to give me plus 2.304 times a. For this one, that's the fourth one, yep. And the next one, we then multiply by 0.67 squared times this number, basically, which will give you 1.024 lots of a. And then finally, we multiply by 0.5 squared, which is a quarter, and that gives me the last piece, which is going to be 0.256 lots of a. So when we add these together, you'll get 26.58 times a as the volume of our step pyramid. Now, a is, of course, the area of the base, which we have here. And I could, of course, work this out, either using a calculator or using my base 2 Egyptian maths. That'd be quite a nice way to practice, see if you can do those two numbers. But what I'm going to do is something I think is a little bit cleverer. We don't need that number, because I know this is 26.58 lots of a, and this one is simply 62.5 divided by 3 lots of a, which is 20.83 lots of a. So if 20.83 lots of a is 275,000, we have 26.58 lots of a, we have a bigger number. And to see just how much bigger, we just look at the ratio of those two. So if I look at 26.58, and then I divide by 20.83, then I'm going to get, I did this one earlier, 1.267. So our step pyramid has a volume, which is 1.267 times this original volume. So in other words, it is approximately 26.7% bigger. as a step pyramid than it is as the regular pyramid. And if you prefer your cold hard numbers, the volume of this one is going to be 350,000 meters cubed. So definitely bigger than if we'd modeled it as a regular slanted pyramid. So there's my recreation of ancient Egyptian pyramid maths. And if you would like to try a calculation like this for yourself, then I suggest trying to work out how the volume of the Great Pyramid of Giza is modified when you take into account the 8 sides of the base instead of the usual 4. And in this case, we would expect the volume of the 8-sided pyramid to actually be a little bit smaller because of that concave nature of those additional sides, though by exactly how much I will leave up to you to work out. Thank you as always for watching. I hope you've enjoyed this slightly different style of video and have learned some interesting history alongside the usual dose of maths. Don't forget to subscribe if you have enjoyed this, and I will see you all very soon. Take care.